Alright folks, welcome to our third and final part of lecture 15 for probability and statistics. So we are now going to begin talking about continuous random variables. We are going to abbreviate this topic a bit so that we can fit in the rest of the material and get into some statistics work with enough time to do justice to it. So we'll cut out a few topics here, but we will cover what is covered thoroughly. Instead of trying to go shallow, we're just going to remove a few topics so that we can get through this material in a reasonable way. So we'll begin with a definition for continuous random variables. A continuous random variable is a random variable whose sample space is an interval of the real line. In other words, it has a continuous sample space. So discrete random variables were random variables with a discrete sample space, meaning either finite or countably infinite. Continuous random variables are random variables with a continuous sample space, meaning their sample space is an interval of R. So that's the fundamental definition. For discrete random variables and for continuous random variables, the sample space was a part of the definition, the collection of possible values. We also needed some way to specify the likelihood with which those values actually occur. So we've got all the values that are possible, but how likely are each of them? That question must also be answered. For discrete random variables, that question was answered by something known as the probability mass function, the PMF. For continuous random variables, we will answer that question via the probability density function, or PDF. So not PDF as in the file type, PDF standing for probability density function. It was our acronym first, and we are keeping it. So the basic definition for a probability density function is that if you start with any continuous random variable x, the probability density function, or PDF for x, is going to be a function. We'd write it with a little f, just like you can write the probability mass function with a little f. But the probability density function is such a little f such that the probability that x lands between a and b is given by the integral of the density function over that interval from a to b. This is the core of the concept. Density functions, you integrate them to find probabilities for continuous random variables. If you want to calculate a probability for a continuous random variable, you're asking about the likelihood that that random variable falls in some interval. You find that likelihood by integrating the density function across that interval. So we've got a couple of immediate corollaries that are sometimes packaged in with the definition, but I am choosing not to. If the integral of these density functions give us probabilities, then these density functions should remain non-negative everywhere. If we ever had one of these density functions dipping below the x-axis in its graph, then you could integrate over the region where that density function falls below, and you would come up with a negative probability value, which does not make sense in this context. So we require them to be non-negative, since their integrals will give us probabilities. And we also require that the integral of the density function over the whole real line be 1. This is analogous to the sum to the, say that again. This is analogous to the equivalence statement for discrete random variables, where we said if you summed the likelihoods associated with all of the elements of a sample space, you would get 1. This is exactly equivalent to that statement. So the intuition for this definition of the density function, this really does look a lot like the definition of probability mass functions for discrete random variables, but the continuous version of a sum is an integral. So actually the integral symbol, the elongated s, is meant to be exactly an elongated s, and it's a stylized s, which is meant to stand for sum. If you think back to Calculus 2, you learned that integrals are actually limits of Riemann sums. And in general, integrals are continuous versions of sums in that way. So for probability mass functions, where we said if you sum the value of the probability mass function at each of the elements of the sample space, you get 1. That is analogous to the statement here for PDFs, where if our sample space for this continuous random variable is the interval from a to b, and you integrate from a to b, and you integrate from a to b the density function, you will get 1. So summing the PMF across all values is 1. Integrating the PDF across all values for the random variable also gives you 1. For continuous random variables, you can calculate probabilities by integrating density functions. That is the core of density functions. That's their purpose in life. They exist to be integrated in order to generate likelihood values. So there may be a bit of confusion here in the previous slide. Let's jump back. I said that if you integrate from negative infinity to infinity, the density function, you get 1. That is true. It's also true that if the sample space happens to be the interval from A to B, then our density function would just be 0 off of that interval. And so the statement in the top right here, that the integral from A to B equals 1, that is equivalent to the statement that the integral from negative infinity to infinity of little f is also 1. Our integrand little f is simply 0 between negative infinity and A, and is 0 again between B and infinity. Another place that we can illustrate the parallel between discrete random variables and their PMFs and continuous random variables and their PDFs is when it comes to the definition of such random variables. For discrete random variables, the definition of any new discrete random variable amounted to a characterization of the sample space and the probability mass function. Those two facts, they are telling you exactly which values are possible and how likely are they each. Equivalently, if you are defining a new continuous random variable, as we will do next time, we'll be looking at some examples next time. But if you're defining a new continuous random variable, it is necessary and sufficient to give the sample space, here an interval of the real line, that's the collection of values that are possible, and you also need some way of characterizing how likely the different values are, and that will be given now by the probability density function. Yet one more way to think about these, and we'll revisit this idea at least a bit, I believe, is that for discrete random variables, where your possible values are separate individual values, if you're adding up probability mass, it's much like taking the mass of individual coins to find, and adding those masses up to find the total mass of that collection of coins. If instead of chopped up coins, you instead have a continuous bar of metal, and you're trying to find the mass of that bar of metal, you would integrate the density function across that bar to find the total mass of the bar. So whereas discrete random variables are something like a pile of coins, a stack of coins, and you can talk about the mass of each individual coin, continuous random variables are more like a variable density bar of metal where the coins have been welded together, say. And now instead of talking about the mass of each individual coin, you have to talk about a density function, which describes how density changes across the bar. So that is another analogy that's very exact, and another way to think about these things. And we'll think about that at least a bit more as we're talking about expected value and variance for continuous random variables. There's a bit of weirdness here that needs to be addressed explicitly, so let us make the weirdness overt. If x is a continuous random variable, then it is true that for any real number, the probability that x equals exactly that real number, I can express that as the probability that x falls in the interval from a to a, which is to say the probability that little a is less than or equal to x, which is less than or equal to little a, and that, according to our definition for density functions, should be given by the integral of the density function from a to a. But that will be 0. If you're trying to integrate some non-negative function from one point to that point again, that integral is always going to be 0. You can see that by thinking about these integrals as area under a curve. So on the left here, I've sketched my density function, little f of x. Along the horizontal axis is my real line, and I've indicated the interval from a to b. So, and this is relevant for thinking about how density functions work in general. So outside of the scope of this weirdness subsection, this picture is illustrative of how density functions give you probabilities. So my random variable x is going to show up somewhere on that horizontal axis. I might be interested in the likelihood that it shows up between values a and b. My apologies if you can hear my bread maker going off in the background. But here we're thinking about, or I might be interested in the likelihood that my random variable x shows up between a and b. I can find that probability by integrating the density function from a to b. That's the definition of the density function. The probability that x falls between a and b is given by the integral of the density function from A to B. Meaning the area that is shaded here in this picture, that is the likelihood that my random variable falls between A and B. So that's a positive quantity for that picture. The likelihood that x falls between A and B looks positive. There's a positive area associated with that interval beneath the curve. But if I think about the probability that x falls between A and A, suddenly that picture has collapsed to a single vertical line, and the area of that single vertical line is 0. So according to that formulation, there is a 0 probability that x equals exactly A, which is to say that x falls between A and A. So there's always 0 probability that continuous random variables take any specific value. That is just a quirk of the mathematical definition of continuous random variables. Intervals have positive probabilities, but specific numbers always have 0 probabilities associated with them. So this can be a bit strange, I grant you that, but it is the way that these probabilities work, with likelihoods defined as integrals being areas under a curve. It's also worth thinking about this picture in the top left a little bit more here. So density functions, we're going to spend a fair amount of time thinking about density functions associated with the normal random variable. We'll start talking about the normal random variable next lecture. But wherever your density function is tall, if you take intervals under the tall part of the curve, you're going to have a higher likelihood of your random variable showing up in those regions. And wherever your density function comes down closer to the horizontal axis, if you take intervals in that region, you're going to have a smaller area associated with such an interval, and that indicates a smaller likelihood of your random variable actually showing up in that region. So if you imagine the bell curve, the standard bell curve that you have a picture of in your mind, it's right there in the middle where the bell is tallest. That's where your random variable is most likely to show up. It's most likely to show up in the intervals of the real line beneath the tall part of the density function, the bell curve. And your random variable is less likely to show up far away from that central region out in the tails where the bell curve gets closer to the horizontal axis. And we will talk more about that next time. So this quirk that says that the likelihood that a random variable is equal to any particular value is always 0, it leads us to the following theorem. If you're dealing with a continuous random variable, it doesn't matter whether you use strict inequalities or non-strict inequalities on either side of such intervals. So we can take a less than or equal to x less than or equal to b. We can consider the probability that a is strictly less than x, which is less than or equal to b. We could take the probability that a is less than or equal to x, which is strictly less than b. Or we could take strict inequality for both of those positions. And all 4 of those probabilities are numerically the same. This follows because the probability that x lands at the endpoints is always 0, and so you're really only talking about the probability of it falling between a and b in all 4 of these cases. And we've illustrated the proof here by showing one of the cases. In particular, we're showing the final of the 3 equalities in the line above. So the probability that a is less than or equal to x, which is less than b, that's just going to be the probability that x equals a plus the probability that it falls between a and b. This would be a consequence of the probability of a disjoint union being given by the sum of the respective probabilities. I could write the event that a is less than or equal to x is less than b as a disjoint union of the events that x equals a and that a is less than x, which is less than b. And because the probability that x actually equals a is 0, we can see the equality of the 2 probabilities listed on the far right of the then statement of the theorem. So the punchline here is that for continuous random variables, you can play it fast and loose with what type of inequality you choose to represent your probabilities in terms of. They're all equivalent. You never actually have any likelihood of continuous random variables landing on any particular spot, and so it doesn't matter whether or not you include the endpoints of an interval when referring to these probabilities. And this is actually going to be somewhat important for us in a bit here. Sorry for jumping ahead of myself right there, but we'll talk a little bit more about why this is going to be of particular interest to us as we move through thinking about cumulative distribution functions, which is, luckily enough, our next topic. So we do have cumulative distribution functions for continuous random variables, just as we did for discrete random variables. We will define them, cumulative distribution functions for continuous random variables. If you've got a continuous random variable and you've got its PDF, then the cumulative distribution function, or CDF, is going to be capital F sub x. The density function is always indicated by a lowercase f, and the CDF is always indicated by an uppercase f. They both have the subscript given by the variable name so that you know which variables CDF or PDF is being referred to. So big F at little x is by definition the probability that big X is less than or equal to little x. That first equality, the first definition there, big F equal to that probability, that's exactly the same definition that we had for that's exactly the same definition that we had for cumulative distribution functions for discrete random variables. The cumulative distribution function is always the probability that your random variable falls at a point less than or equal to the input value for the CDF, little x here. When we're dealing with continuous random variables, that probability can be computed by an integral of the type that we've just been discussing. Oops, sorry about that. So because for continuous random variables, probabilities of intervals are always given by the integral of the density function over that interval, this cumulative distribution function reduces to the form given on the far right of the definition here. The value of big F at little x is going to be the integral from negative infinity up to little x of f sub x, x prime dx prime. So you can calculate the likelihood that big X falls less than or equal to little x by integrating the density function for big X over all values that are less than or equal to little x. This is of the form a less than big X less than or equal to b, where we have taken a to be negative infinity and b to be little x here. It's also worth noting that I'm letting my little x value be my integral is taken with respect to little x prime, so I have a dummy variable of integration which is different from little x, which is the upper limit of this integral. So the idea, we can look at this image in the bottom here, and we're going to talk more about this image later on. But the idea is that little x is a fixed value on the horizontal line, and we're integrating from negative infinity up to that little x. My dummy variable of integration, x prime, is going to slide along the horizontal axis from all the way in the left at negative infinity and move right, adding up values until it gets to little x. You can imagine a bead on a string, and it's starting far off to the left, and it's sliding to the right, and every pace or so it takes a Riemann term, like a rectangle, and then it moves a bit to the right and it forms another rectangle, and it moves a bit to the right and it forms another rectangle. It continues to do that until it gets to little x. It adds up the value of all those rectangles, and that's its approximation to the area under the curve. And then you repeat that process with smaller and smaller jumps each time until you have the actual limiting value, which is the true area, the integral. The big picture point of everything that I'm saying is that if little x is the right-hand endpoint of that interval, we need another variable that's going to move from negative infinity up to little x, the bead sliding on the string, and that's our x prime. You can also use y, you can use z. It just has to be different from the variable that is the upper limit of integration. This one was got to be an x prime because I forgot and I wrote little x in, and then I had to come back and add the prime marks to make it different from the upper limit of integration. So intuitively, the cumulative distribution function always tells you how likely is it that your random variable falls to the left of the input value to the CDF. If you're taking big F at little x, then you are getting back a number which tells you the probability that your random variable falls to the left of little x. It's always the area of left-hand tails associated with the density function. So this image that we've drawn in parentheses looks something like a density function for a normal random variable. We'll be talking about those next time. They do have the classic bell curve shape. And if I take the CDF of such a random variable and I evaluate it at point little x, what I'm asking is how likely is it that my random variable falls to the left of little x? That is, by definition, given by the integral from negative infinity up to little x of the density function. And we learned in Calc 2 that the integrals of non-negative functions of this type are the area under the curve, between the curve and the horizontal axis. So saying big F at little x, when I write that down, that is equal to the probability that big X falls to the left of little x, and that's given by the integral of the density function from negative infinity up to little x, and the integral of the density function is the area under the curve that is the graph of the density function. So there's a lot of different ideas going on there. We've connected some ideas from Calc 2, the fact that integrals are areas under the curve. We are connecting this basic idea about density functions, that integrating density functions gives you probabilities. And we're also considering the definition of the cumulative distribution function as a probability of the random variable falling to the left of little x here. So, another theorem concerning cumulative distribution functions is the following. This actually holds equally well for discrete or for continuous random variables. And the theorem says that the probability that a is strictly less than x, that is a strictly less than symbol, which is then less than or equal to b, is going to be the value of the cumulative distribution function at b minus the value of the cumulative distribution function at a. So we can find the likelihood that x falls in an interval of this type as the difference between the values of the cumulative distribution function at the right-hand endpoint of the interval and at the left-hand endpoint. So we can actually prove this in some sense for continuous random variables, a proof by picture at the least. The probability that big X falls between a and b is going to be given by the integral of the density function from a to b. That is the definition of density functions for continuous random variables. More basically, that's how we always calculate probabilities for continuous random variables, by integrating the density function over the region in question. The integral from a to b is going to be given by the integral from negative infinity up to b minus the integral from negative infinity to a. That's actually what we're trying to illustrate in the pictures at the bottom here. That on the far left of these pictures, I've got the area under the curve from a to b. That would be the integral of the density function from a to b. I could compute that by taking the integral from negative infinity up to b, meaning the whole of the area of everything to the left of b, and subtract from that the area of under the curve to the left of a. So if you take the middle picture and you subtract it out, the farmost right-hand picture, you would be left with the picture on the left there. It's like taking the middle image and chopping off the tail to the left of a and being left with just the region between a and b. So that's the idea in the second equality in our proof, and the third equality is just the definition of the cumulative distribution functions. I'm finding it difficult not to ask you folks if you have questions as we're going through this material, which should highlight the fact that I do welcome questions. I do want you asking questions if you have them, so feel free to email me questions about any of the lectures, or show up to our virtual office hours that we will start hosting on Thursday and bring questions. It is not in my nature to lecture without soliciting questions from the audience, so please bring them to me in whatever way you can manage if you have them. So this fact that you can, well, one thing to say is that this theorem here is stated for a strictly less than capital X, which is less than or equal to b, but as we just said, for continuous random variables, it doesn't matter which inequalities you use. So we have to be careful with which inequalities are used if we want the theorem to be true also for discrete random variables. But actually, and the theorem is true for discrete random variables when stated this way, but we didn't mention it when we studied discrete random variables because we don't care as much about it for discrete random variables. It is going to be particularly important for us in our study of the most important random variable that we will study in this course, which is the normal random variable. So really, we care about this theorem for normal random variables. Normal random variables are continuous random variables, And for continuous random variables, it doesn't matter which inequalities you use. So I can state the formula in the way that it's given in the top right here, with both being less than or equal to symbols, as long as I'm doing it in the context of continuous random variables. And we're going to use this formula heavily when we're dealing with normals, which we will do next time. And the final thing that we want to say today is to illustrate the connection between cumulative distribution functions and probability density functions. So we saw during, or we at least stated, and depending on which course you're in, we may have looked in greater detail at the fact that for discrete random variables, knowing the density function, knowing the probability mass function for discrete random variables, and knowing the cumulative distribution function were equivalent. If you knew the probability mass function for a discrete random variable, you could find the cumulative distribution function. And if you knew the cumulative distribution function, you could use that information to generate the probability mass function. To know one is to know the other. The same is going to be true for cumulative distribution functions and probability mass functions in the arena of continuous random variables. But here, the connection is actually more explicit, and it's given by this theorem. In fact, the density function is the derivative of the CDF, which is to say the CDF is the antiderivative of the PDF. So these two functions are connected by this calculus-based relationship. We had defined the big F to be the integral of little f, and so it follows naturally that little f must be the derivative of big F. This is part and parcel of the fundamental theorem of calculus. Integrals and derivatives are inverse operations. So if the integral of little f is big F, then the derivative of big F must be little f. All we're doing here in the proof is we're unpacking the definition of big F, and we're applying the fundamental theorem of calculus. Generally, what's stated is the fundamental theorem of calculus part 2, depending on how your calculus course was structured. But the idea that the derivative of an integral of this type, where the right-hand endpoint of the interval is the variable that you're differentiating with respect to, when you have that situation, you just get the integrand's value at that right-hand endpoint. So the derivative with respect to x of an integral from negative infinity up to little x of little f is just little f at that right-hand limit of integration, little x. So let me know if you have questions about any of this material. It is looking like we are going to be able to move a bit more quickly. I'm not just going to cram the full 75 minutes that we usually have for lecture full of video, because I imagine people will be pausing and looking at sample problems or looking back over material that we've covered. Like if something is unclear and you have to pause and back up a bit, I want you to be able to have the time to do that and still cover the lecture within 75 minutes. We will move quickly through the end of the course, but you may expect that the total of our video times adds up to about an hour or so, giving you some time to review portions of the lecture or to try to work out some sample problems before you proceed to the solution that's given in the lecture. Next time we will be thinking some more about continuous random variables in general. We'll think about expected value, we'll think about variance, and we'll look at some examples before moving on to the most important example, normal random variables. We should cover normal random variables with the end of our next lecture and our first lecture from next week. And after that is covered, we will move directly into statistics. So we should easily be able to spend our last 4.5 or 5 weeks on some statistics material. Alright, I thank you folks. I will see you again next time. Many thanks. Have a good night.